Okay, so this video is designed to give you a little bit of help on the analysis section of the Advanced Kinematics video for Bosco Tech AP Physics. Or the Advanced Kinematics Lab for AP Physics. During the demonstration videos, the pre-lab videos that I showed you, I collected these 4 data points. The inclination of the slope is 9.5 degrees, the length of the slope is 46 centimeters, the length of the level portion is 82.10 centimeters, and the time required for the ball to move down both portions, both the slope and the level, is 1.768 seconds. I hope by now you realize that you have 2 distinct types of motion. Of course, you have the slope and you have the level. These 2 different types of motion, these 2 different phases of motion, each have a corresponding kinematic system that it works with. So as you descend the slope, descending, either sliding or rolling down a slope with constant incline, like this one, is an example of motion at constant acceleration. Rolling across a level surface means that there's an equal amount of force upwards and downwards, equal forces, equal and opposite forces rather, means that there is no net force. No net force means that there is no acceleration. No acceleration means you have constant velocity. Okay. Each of these has a corresponding problem-solving system. Motion at constant acceleration deals with 5 kinematic variables: displacement, initial velocity, final velocity, acceleration, and time. Meanwhile, motion at constant velocity deals with only 3 variables: displacement, velocity, and time. All right, let's look at the displacement during the motion at constant acceleration phase. In other words, as it descends the slope. We know that it traveled from here to here, crossing a length of 46.00 centimeters. So that's going to be our displacement, 600 meters. Our initial velocity, well, the whole thing we did with the pin, or dropping the ball in, holding it there, releasing it with the pin, that is designed to make sure our initial velocity is 0. Our final velocity, we don't know what that is, but we can relate it to quantities over in the constant velocity side, so it pays to give it a special variable. We'll just call it V1. We don't know what V1 is, but we do know that we can relate it to portions of the constant velocity side of the equation. All right, acceleration, we don't know what that is, nor can we relate it to anything on the constant velocity side, so let's just not care about it for now. Time, we don't know what that is, but we do know that the time required to do this motion and the time required to do this motion, we'll call this T1, we'll call this T2, those 2 add up to the total time measured by the photo gate. In other words, T1 plus T2 is 1.768 seconds, which means that T2 is 1.768 seconds minus T1. Just do a little bit of algebra in your head, you can figure that out. Okay, next up, the displacement across the level surface is 82.10 centimeters, so that's going to be 0.8210 meters. And our velocity, we don't know what it is, but we do know that we called the velocity at the beginning of the level surface V1, which means that the velocity at every other point along the surface is also V1. And the reason for that is that velocity is constant. Okay, this is a good place to be at, because you've got motion at constant acceleration with 4 out of your 5 variables defined as either exact quantities, as either known quantities, or in terms of variables that you can relate to the other equation. So we've got 2 unknowns here. We can construct an equation which relates that to that to that to that. We have the same 2 unknowns showing up here, and we can relate it. We can construct an equation which relates that to that to that. That means that we have 2 separate equations and 2 unknowns in those 2 equations, which means you can set up a solvable system of equations. But the translational story is not the only portion of this lab. The added complication is that we used a round object, and instead of sliding down the slope, it rolled. So we have a combination of translational and rotational motion. Throughout the entire portion, we have some sort of rotational motion. Now, there is a reason why I didn't give you steel balls or glass marbles. Those rubber-coated mouse balls they basically have grip, just the same way a tire has grip. And since they rolled with some grip and rolled at reasonably low speeds, it is an excellent assumption that throughout the entire motion we had rolling without slipping. This is good news, because if you're rolling without slipping, then we have 3 equations that relate our translational quantities to our rotational quantities. Namely, distance moved is equal to angular displacement times radius. Hope you got the radius of the ball. Translational velocity is equal to angular velocity times radius. Translational acceleration is equal to angular acceleration times radius. Okay, so if I asked you for any angular quantity, probably the easiest thing to do is first, and easiest does not mean easy, but the most straightforward way to do it is to set up this system of equations in the translational system, solve it, use that information to figure out whatever translational quantity you need, then feed that translational quantity through these equations in order to get the equivalent angular quantity at that same point. Now, one other thing I should note is that your angular displacement is not the inclination of the slope. Just because they are both angles does not mean they are the same. The ball went through many, many rotations, probably 10 or 20 rotations. That's going to be somewhere between 3,600 and 7,200 degrees, whereas the incline of the slope is just 9.5 degrees. So, in fact, the incline of the slope does not show up anywhere in these equations, or at least not yet. So, notice I haven't, so that's the end of this hint video. I've shown you how to set up the translational system, shown you how to get from translational to acceleration, translational to rotational quantities, and the rest is up to you.